Hello everyone, thank you very much for attending this presentation. My name is Dimitri. I'm a postdoctoral researcher at University of Geneva, and today I'm gonna talk about Swift's type system. Swift is a programming language developed by Apple to be a successor to C family languages such as C, C++, and Objective-C. It is being used in a broad spectrum of applications, obviously including graphical apps for iOS and macOS, but also since it released as an open source project in 2014 in other domains such as web services and artificial intelligence. From my own experience, Swift is also a very good first programming language. I personally teach formal verification methods to second-year bachelor students using Swift as an implementation language. One strength of the language is its relatively rich type system compared to equivalent mainstream alternatives, which allows for clear and expressive APIs. While preparing this presentation, I thought that the best way to illustrate this point would be to present a real-life application rather than a mundane school example as those you may find in online tutorials. I guess most of you are familiar with the concept of parser combinators. Roughly speaking, parser combinators are based on the idea that a parser is nothing more than a function that consumes an unparsed stream and returns a parsed element along with the remainder of this stream. One can then compose parsers to create more complex ones, eventually producing a function that is able to parse a complete grammar. I developed a small library called Diesel that implements this concept in Swift. Here is a usage example that illustrates a simple parser for floating point literals in some fictional language. Line 3 declares a simple digit parser as a function that consumes a character from a substring if it satisfies the isDigit predicate. This merely checks if the character is a number from 0 to 9. The parser is then composed with others to create the number parser. The entire expression reads as optionally parse a minus symbol followed by one or more digits, optionally followed by a dot followed by one or more digits. Finally, we use the number parser at line 8 to successfully parse minus 12.43. Hoping I won't sound like I'm shamelessly promoting my own library, I think we can agree that this looks like a reasonable piece of code that captures the essence of a relatively abstract concept with a clear and concise API. So how does this work under the hood? Well, most of the library is built on this parser protocol. A protocol describes a set of property, method, and associated type requirements which a conforming type should implement. This is one particular instance of a more general concept that is common in many programming languages. For instance, Java has interfaces, C++ has abstract types, Rust has traits, and so on. The protocol here has two abstract associated types that represent the type of the element being parsed and the type of the string from which they are parsed. The protocol also contains a single method requirement that requires conforming types to implement a method that accepts a stream and returns a union type modeling the possible success or failure of the parser. Here's an example of such a conforming type. The conformance is declared here. It instructs the compiler to statically check that element parser does indeed satisfy all requirements. We also add additional constraints on the concrete type that is used to fill the associated stream type. We require that it conforms to collection, which is another protocol declared in the standard library, and that subsequences of this collection be of the same type. Without getting too much into the details, this requires that the views within the collections be of the same type as the collection itself. The parse method is declared here. Unsurprisingly, it just attempts to pull one element from the stream and checks if the predicate holds. If it does, then the parser succeeds. Otherwise, it fails with a parse error. We use yet another feature of Swift, called retroactive modeling, to generate the final API. This allows us to extend existing types with additional behavior. We use it here to extend the collection protocol when its subsequences are of the same type, to add a method letter that accepts a predicate and creates an element parser. The benefit is that the user code is now very flexible without any sacrifice on type safety. We can easily swap the shape of the stream that we want to parse, or even the contents of the stream, with very little change to the user code, if any at all. Let's quickly recap the features we used. We obviously used protocols and protocol inheritance to describe abstract type requirements. We used associated types to describe abstract relationships. We used bounded polymorphism to constrain these relationships. We use subtypes to refer to conforming types, which is not as trivial as it may seem. I'll come back to it later. We use retroactive modeling to extend existing types with customized behavior. And finally, we use a lot of type inference, but fortunately this last one was for free. I think it's safe to argue that what I've just presented here is relatively complex, at least for the inexperienced developer. It's not that much of a problem if I put my library design hat. I don't mind writing complex code as long as I can keep the user code relatively simple. But this is a little deceiving. As a user, it can be frustrating not to understand why my seemingly simple code does not work when all the compiler has to offer is some cryptic message about associated types or any other obscure feature. I think anyone who has used Boost templates in C++ knows what I mean. One issue is that the abstraction level is higher than that of a typical object-oriented patent. As an example, let's have a quick look at the definition of the equatable protocol from the standard library. As one can expect, this protocol only defines two requirements for equality and non-equality. Using a Java-based reasoning, it's reasonable to think that the last line is legal, yet it fails at compile time in Swift. This might be one of the most common questions I've received from students. The reason is that self is not a mere alias on equatable, but refers to the conforming type. Therefore, conforming to equatable does not make you equatable to all other equatable types, just yourself. The last line fails because of what it implies. We can't actually infer anything about the interaction between two expressions that merely conform to equatable because the actual conforming types might be completely unrelated. One problem in understanding this kind of situation is that the documentation is provided only in the form of examples. Hence, it is difficult to get a general and deep understanding of the semantics. Instead, users are pushed to project their own assumptions onto the language, usually adapted from their experience and understanding of another language. Inevitably, this can lead to widely incorrect conclusions. If I put on my researcher hat, then there is yet another big problem. Specifically, that examples alone can't be used to outline an unambiguous semantics. This prevents us to reason about soundness, and also means it's difficult to foresee how future features may interact with existing ones. The solution is obvious: let's formalize everything. But Swift is a very large language, and it will be difficult to formalize everything almost from scratch. Instead, we propose Featherweight Swift, following the proud tradition of formalizing core languages. You can think of Featherweight Swift as a light version of Swift that focuses on the features of its type system. We ignore non-member functions, computed properties, exceptions, concurrency, or even side effects. One other feature that was cut are generic types. Although they play an important role in Swift's type system, as we saw in the introduction, they added a lot of complexity and were not strictly necessary to explain the basics of protocol conformance. What we kept includes protocols, classes, and extensions, along with retroactive modeling. We also tried to keep Featherweight Swift as close as possible to real Swift so we could copy-paste programs in an actual Swift compiler. This was very helpful to the design of the formal semantics, as it allowed us to test assumptions against a reference implementation. I realized that presenting a formal semantics in a conference setting might not be the sexiest thing, so don't worry, I won't go over every detail. Instead, I just want to focus on this rule, which summarizes Swift's method lookup. It is important to note that, although a derived class does inherit the conformance of its superclasses, protocol conformance must be checked in the class itself. This relates to the point I made earlier about self-types, among other things. It follows that method lookup work along two orthogonal dimensions. One relates to protocol conformance. The first step is to get the set of conform protocols in order to collect all methods defined in protocol extensions. I didn't mention this earlier, but we can associate protocols with different implementations of their requirements that are inherited by all conforming types. Then we move to the second dimensions of method lookup and get the set of methods declared in the class hierarchy. Note that this does not include the methods inherited by protocol conformance in superclasses. These are already part of MX. We merge the two sets with this operator, which models the shadowing of the default implementations. Finally, we instantiate self-types. Notice that this is done in the derived class, not in the support class. A lot of our effort has been to kind of guess the semantics of the reference implementation. The code of the compiler itself is a valuable source of information, but it is a very large and highly optimized piece of software from which it is difficult to establish a complete semantics. We discovered a lot of interesting things with this process. Some were non-impactful limitations, mostly due to implementation choices, but others were actual bugs, and I would like to end this presentation by discussing one of them. This is a relatively simple piece of code in actual Swift. It defines a protocol boxable that requires the method boxed, which takes no argument and returns an instance of the conforming type. I want to conform to this protocol with a class list that is a very straightforward implementation of a linked list. The compiler will correctly refuse this program because derived class cannot actually inherit this method. As this was formalized in the rule we saw earlier, it will not satisfy the self-requirements from the protocol. A trivial solution is just to prevent subclassing. Here, the keyword final has a similar semantics as in Java and asserts that lists cannot have subclasses. But I really want to subclass my class, so I can follow one suggestion from the compiler itself and use a self-type. The use of a self-type is more limited in a class than in a protocol, but without going through all the details, it basically refers to the derived type at runtime. Unfortunately, while the method signature is now well typed, the code still does not compile. This time, the problem is that returning an expression of type list is obviously incorrect when self refers to a derived type. As I'm growing tired of these errors, I just add a false cast and promise myself I won't do anything stupid with this code. Anyway, I've been told Swift catches invalid typecast at runtime, so my extensive unit test should reveal any problem, right? It turned out this case was actually not handled. Don't worry, it has been since fixed. Before I close, I would like to quickly address a common concern about featherweight formalizations. It is clear that what we have here is a very restricted subset of Swift that cannot be used to reason about bad interactions between all the features of the language. But I believe the explanatory power of a simple formal framework has a lot of value nonetheless, as demonstrated by the bugs we found. Despite all the elided features, Featherweight Swift is still able to explain a lot of tricky situations unambiguously, some of which are very unlikely to be featured in documentation examples. Alright, that's all I've got for you today. Thank you very much for your attention. I will be happy to answer any question you may have. Otherwise, I'll just leave you with this very inspirational quote.